Testing.
So I guess I should start. There are several things that try to remind you. First would be that your homework one will be due on the end of the Friday. So please make sure you submit that. Homework two, I will probably release today, but it will be again given 10 days after Friday. So if you start, I mean, basically more, it is like 2 weeks from now, but it's more like the due date I will set probably 12th of October. But I mean, you just count 10 days from Friday. So probably 10 days from Friday. So I think it's sufficient time, and then just to do that. I mean, I will probably release today. And second thing I want to say is about the text. So it's, as I said, it's on the Friday of the last week of the semester. Is 2nd of the December. So please go there to fill in, because we're going to book the room there. So that will be our only test that will be there. And then some of you asked for the past year papers, then I will put that later as we probably in October sometime. Put them on the web. And the goal today, as I said, is just we have to finish the probability, okay? And mainly we'll finish the base rule and also the combinatorics, and we'll start some probability. So we'll finish this and have something on the random variable, okay? So to begin, let's very briefly review what we have been doing for this topic. And we start from the idea of classical definition of probability as a long-run relative frequency, which means if you try to repeat the experiment many times, then just look at the ratio of the frequency where it's favorable to those events. So that is the idea. And then next we define them using axiom, right? So with axiom one said probability must be between 0 to 1, and probability sample space must be 1. And the lastly, this is the most important thing, says probability of an event will be sum of probability of each outcome if each outcome are mutually exclusive. Okay, and the union become the event, right? So that is the main thing, and it derive all the rules we want, right? Say like the complement rule, and we have the addition rule. We also have the total probability rule, right? And then next we define the conditional probability, right? Which is defined as probability of event A given B will be a fraction, the numerator is A intersect B and the denominator is B. And the reason, just to remind you why you want to divide them, divided by probability B, because you have to satisfy axiom 1, which said that probability must be between 0 and 1, right? And also axiom 2, which said the probability of sample space must be 1, right? Because knowing that B had happened, right? So if actually A is B, right? So you want this guy to be 1, right? So that's why we really need to have this to divide them to normalize, because the reason is the sample space shrinks, right? Because before it's like the S, but now it's just like much smaller. So before it's like the big S, now it shrinks. So everything shrinks, so that you have to divide to rescale everything correctly, right? So that is the main thing, to basically expand the thing so that everything make up is probability 1. Okay. And from the definition of conditional probability, we have the multiplication rule, which sets A and B is A given B times B, or B given A times A. So that would be the main thing. And the next thing we learn is the independence. Okay, so it says if the two events are independent, if telling you B cannot help you anything about A, right, or vice versa, or the intercept is just the multiplication. Okay, so that is turn out that the very last one is very important, as we actually rely on this, okay, a lot for our all the subsequent learning. Okay, but anyway, so let's go to the most important thing we want to talk about. Is called the Bayes theorem, right? What the Bayes theorem is, somewhat you are swapping the two, okay, swapping the two, and you are trying to change it, okay, swap them, and what do we learn from that? Okay, so slightly a little bit more tricky, right? But the derivation of this is not complicated. It is simply coming from the definition of conditional probability, right? So this is by the multiplication rule. This is simply just this guy, just probability A intersect B. Okay, so so that's why it's exactly the same thing here. Okay, I don't see should not be difficult in terms of math. So the most important part is trying to understand the main uses of it. Okay, one of the main use is what we call the Bayesian update. Okay, so this is applying that. So let's recall this. I think we talked about this on Monday as a setup, but let's actually solve this problem, and you will appreciate why we need them, and this is very useful. So let's do it again, because I guess Monday still probably you don't recall all the details. So basically, it's where 40% of the population is infected. Okay, so that means that if I try to pick up a random guy in the society, 4 out of 10 people are infected. Okay, so without doing anything, it's 40%. Okay, so the question is there any way we can improve this, right? So the idea is what we call, you have a medical test, right? And this, you can imagine, this is a new information. Okay, so here we try to incorporate new information. Okay, if we have a medical test that is perfect, okay, then there's no question already. So if everything is perfect in this world, you test positive, they have the disease, negative, no disease, then you're done, right? So the question is more like if we don't have a perfect medical test. So what can we do about that? Okay, so in this question, what we have is if the person is infected, okay, a positive result with 0.8, right? So and then if this one is unaffected, then positive result with 0.4, okay? So sometime in this case, it might be fruitful to look at a matrix, maybe we call contingency table, right? So, or somewhat similar contingency. So the column, whether the test is going to be test positive, negative, right? And then they have disease, right? Has or don't, okay? So if he has a disease, right? So 0.8, you get the disease, right? And if a disease negative, then will be 0.2, you have a negative result, right? If the guy is not infected, it will still have 0.4 that positive, but 0.6 is not, right? So and in the notation, we call it this A, right? And don't means A complement, right? And we call this B positive, right? So so if you try to do this like what we do in the contingency table, this is what we get, right? So you can imagine that where you come with this number actually come from the contingency table, right? If you have the test, you have enough number of sample, you have the contingency table, and then you divide it by the total number of the sample or subject you're doing, then it is what you get, right? So now the question is more like the following, right? Is asking the probability infected given positive result. So they basically just like asking this, right? You have a positive result, you're asking whether it's infected, okay? So that is the question we're working on. And what is given is this three numbers, okay? These three numbers, okay? And we are going to try to apply the Bayes rule, okay? And to apply the Bayes rule, you do notice that the Bayes rule, the denominator is what you're conditioning for, right? So the first thing you should check out is we need to figure out what is probability B, okay? So this is something we need to calculate, right? Because remember this, right, will be use the Bayes rule, right? It's the probability B, right? And probability, you swap them, B given A times A, right? This is the Bayes rule. If you try to check out the slide in the previous pages, then this is what we want. So the denominator is something we would like to calculate, right? Probably B. And how to do it is we use it, the total probability rule, right? Will be just this probability B given A, okay, times probability A, okay. So you basically divide in two parts. The first part is related to A. The second part is not related to A. Okay, so that is the expression. Okay, so we first calculate the denominator, which comes from the idea of what we call total probability rule, right? So, but that is just simply B with A and B without A, right? The first part is B with A, right? Because the first part is exactly, if you recall, this is just simply probability A intercept B, right? And this part is just, the second part is just probability A complement intercept B, right? So basically just the first part is A and B, right? The second part is A complement B. So it's B with A and B without A, right? So because with A and without A are mutually exclusive, we can just divide them into two parts and we analyze separately. Okay? Is there any question for this one? I mean, all the calculations actually in the next slide. I mean, but I just put in the same slide there. It's already in your notes, so you don't really have to copy, but it's already there in the next slide. But I just put it here because easier to show the result. Okay. So the first guy is B given A is already 0.8. Already have the answer. We already have the answer. This is 0.8, right? This is 0.8. Okay. And A is 0.4. Okay. So that would be not an issue. Okay. And this one, B given A complement already there also is 0.4. Okay. And what is left is what is probably A. Okay. And actually we know it already, right? Because A and A complement are complement, right? Mutually exclusive is exhaustive. And use the complement rule, that's 1 minus 0.4, right? That is 0.6. Okay, it's coming from this guy. That's how we derive that. Right, so that is how you derive that. Is that clear how we end up with these 4 numbers? Is it clear? Is that a question? Okay. So then it will become now clear how you get the numerator, okay? Because the numerator is nothing but the first term, okay? Same as the first term. So what you get is just 0.8 over 0.4, right? Over 0.8 over 0.4 plus 0.6 over 0.4, right? So basically it's just this one, okay? That's nothing but this guy. And the answer is already on the next slide. But I'm trying to tell you what you learn from here, right, is, and this guy I think is somewhat like 0.5 something, okay, 0.51 or 0.57, 0.5 something. So what you learn from this is, before you have a random guy you pick up, then the probability is 0.4, right? But now after a test result where you are notified the person has a negative, so for a positive result, right? Then you're likely to think he's more likely to have the disease. Now you revise upward from 40% to 50%, right? So that is what you learn from that, okay? So of course, I mean, I didn't show it here, but you can definitely calculate what happened if the guy have a negative result. Okay? You can definitely do it at home. Try to do it yourself for that. What if the negative result? And it will be less than 40%, right? Because you learn it the negative, then it's likely less than 40%, right? And if you really want to challenge yourself, you can try to think about what happens if you, once you've done a positive test and do another one, also positive, what is the probability? Okay, of course, it's more than 0.5. Okay, and probably the question would be even more challenging is how many medical positive tests before you can conclude that he has a disease, right? So suppose you have a rule saying that more than 90%, then you say yes, or 80%, then how many tests is needed to make sure that you confirm? So that would be something that you can try to figure out. But of course, there are much more advanced than, not more, it's more involved than we do. I mean, you have all the technique, but we're not asking that much. Okay, I mean, we're just asking for the first round for our main purpose, but you can think about those. Okay, that would be something you would want to understand, and you can see how information change our belief or our initial what we know. Okay, so we know randomly a random guy 40%. If you keep testing that guy, and sooner you will know, right? Because I mean, if you keep doing enough tests, then you are pretty making sure that things would be more clear after enough experiment. Is that clear what we're doing? Is that okay? I mean, all the calculation is already on the slide, so it's already in this slide. So if you happen to miss it, doesn't really matter, but it's already there. So this is the calculation result. Okay. So to give you a perspective, what's going on here, you can look at the tree diagram. Okay. So the question asking the guy is whether they're infected or not infected, right? So you pick a random guy, 40%, they're infected, all right? So that's why it means this is 60%, okay? This 60%, right? And the question is, you actually don't know whether you are here or you are here, whether you are in red or you are in blue, okay? So maybe I use blue to make sure everything is more clean. So this is 0.6, okay? So you are not sure whether you are blue or red, right? If you pick up a random guy, okay? If you don't do a test, that's the best you can get, okay? Now suppose you do a test, okay? You do a test. And the test, you don't know where it is, but you know if the guy has disease, right? Then 80% you end up with the top branch, okay? And with the complement, which is 20%, you end up with the second branch, okay? And if the guy have no disease, right? 40% is positive and 60% negative, right? So now first we complete the tree diagram first, right? How to get this number, right? You use the multiplication rule, right? Just multiply this to this, right? Then will be 0.32, right? Because it's 0.8 times 0.4, right? That is the multiplication rule, right? Then if to this guy, you multiply this is 0.08, right? Right. And for this, how to get this guy the same? You just multiply backward from the tree, from 2, 4. Okay. Here is 0.36. Okay. So everything add up to be add to 1. Okay, because it must be one of the branches at the end of the day, right? So now the question is probably we try to see from the base rule perspective. Okay, the question now is we see the guy has a positive result. So what we're looking at is we know that what is going on is this part is irrelevant. This part is irrelevant, right? Because we know that guy is positive, right? So what we left is only 2 branches of tree. Okay. So the question is, we see that the guy is positive. How likely he has the disease, right? So asking what happened is asking we have this branch and this branch. Okay. How likely is come from here? So how likely is this branch? Okay. So that's why look at 2 branches, asking whether is how likely is the above. So that's why likely is this 0.32 over 0.32 plus 0.04, right? Because you don't know, it's a ratio, right? So relatively, which is because the total is 0.32 plus 0.04, right? And 0.32 is whether you are in the first branch. Okay. The question is, let me repeat the base rule here, right? Is you know it must be coming from the first and the third branches. Okay. The question is asking how likely is from the first branch, right? So just the ratio, right? It's relative ratio. From 0.32 is coming from the top branch, right? And 0.24 is just adding up the 2, okay, comes from for the denominator. Okay. So that's the base rule. from the perspective of looking at the branches, right? Because you know that the second branches and the fourth branches is unrelated, right? So we're asking what is the probability that you are in the upper branches, right? So you're either the first branch or third branches, okay? Asking how likely you are in the first. So basically that's how you update. Is that clear what we are doing? Right? Of course, we can basically blindly follow the formula that will be there, but I hope I convinced you this is a easier way to visualize the problem. But of course, you can always rely on the formula that you can just do it without any issue. Is that okay? Any question? I guess this is the one of the most complicated thing we're trying to learn, at least for the first half of our course. I think things are more difficult for the second half, but this is the most difficult for the first half of our class, our course. Is there any question? Because the base rule is somewhat is very deep, right? As we said, this is invented, I think it's 1920s, right? Only hundreds ago, right? And the probability have been invented like long time back, 300 years ago. So so this is something worth looking at carefully. Okay, if there's no question, then we will say goodbye to our base theorem. Okay, and then we will so this is the general version. Before we have just finally before we do that, it's just like here is I have a B and B complement, but I consider partition that the same idea goes on. Okay, here what I meant is here I have only two branches here. Okay, A and A complement here, yes or no, but potentially you can divide it into many parts, the same idea. Okay, just to make sure you understand, right? Because basically it's like this, right? Suppose you have another one, another one. So the same rule apply here. Is that clear what's going on? But I mean, since it's technical, so I don't want to talk about too much, but you can easily generalize this to more general concept. Is that okay? Is there any question? I mean, of course, you might have, but if you are not, you're assigned to ask right now, I mean, you can ask me during the break. So what is left is somewhat little bit more relaxing. It's just counting. Okay. So some of you might have learned it in the primary school or even high school. So that's counting things, and it's more fun, I would say. And the counting actually related to probability and related to what we trying to talk in the random variable. Okay. So let's consider the case we have with a mission where we have two tasks. Okay. And you do the first task first, and then the n1 number of ways to do it. And for the second task, you have n2 number of ways to do it. The question is how many ways you can do it is n1 times n2. The reason is being you were just listing a table, right? You're just listing a table in your mind, right? To do the first task and second task, right? It will be 1 up to n1, and there will be 1 up to n2, right? So each combination is possible, right? Each thing in the cell is possible. So that's why you multiply n1 times n2. Just simply what you learn from the multiplication, right? So I mean, to give you a more concrete, and we'll talk about the generalized version, right? First. So if there's a k different tasks, and each I task have ni way to do it, how many different ways to do it? You just multiply them together. Okay. So it is very simple thing, right? There's nothing new. I mean, you have learned it in your high school or even in elementary school, right? That's why you can that's how you learn multiplication, right? That's how you do counting. Okay? That's why the principle of counting. So let us see the example that motivated from my experience when I was studying as undergrad like you 10 years ago. So when I was a student, I was rather don't have a deep pocket. I mean, still now I'm rather relatively poor. So the question is like one thing about good thing about CHK is a many canteen, and the canteen offer very budget meal, right? So-called 頹飯. So what it means is at my time, there are food in the canteen, and at that time, the price of normal menu would be $20. Okay, now I mean it's unthinkable, but at that time, this simple meal will only cost you $10. Actually, in the CC canteen, it's just $9.50 at my time. So I mean, it's actually it's a pretty good one. You can see, you can choose either two dishes, rice or noodle. I mean, noodle actually means spaghetti at the time, and you can out of that you can actually have a lot of protein. You can get pork, you can get beef, you can get chicken. Okay, pretty good. And I mean pork. I think the luncheon meat. Okay, and different sauces you can use. You can black and white and red. Okay, the question is, a poor student like me, I mean, would feel bored if I had the same thing every day. I mean, some of you can eat the same food every day, but I try to like something. Some rotation is better than always the same thing. So the question is, how many days I can rotate? Okay, I mean without repetition. All right. So the question is, how many dishes can be made from this choice? Okay, and this budget meal actually in CHK appear in every canteen, and every canteen has some slightly changes. I think this is coming from the CC canteen. I think. So how many way you can fill up your main dishes is rice or noodle. So two choices. And how many different way you can choose the meat, right? 3. Okay. How many different way you can choose sauce is 3. So it's 2 times 3 times 3. Okay. So 2 times 3 is 6. 6 times 3 is 18. So you have 18 way to repeat, right? And assuming actually you don't go to school every day. I guess not everyone go to school. Probably go to school 4 days a week, right? So probably it lasts for 4 weeks, basically a month, right? So it's really good, right? Every month you have I mean you only repeating yourself only for every month, right? We only have 13 weeks, right? So basically you only eat the same thing 3 times in a semester. Okay, so we're pretty good. Okay, so here I don't include drinks because I'm not that rich to have drink. But if you are willing to spend a few more bucks for drinks, then probably you don't have to repeat yourself in the whole semester, right? Suppose you have 4 different drinks at a time, probably lemon tea, lemonade, and coffee and milk tea. Then of course you already don't have to repeat yourself for the whole semester. Okay, so and this become increasingly relevant now these days. Probably this kind of meal getting increasingly popular in Hong Kong, even in the CBD area. Anyway, any question? How you calculate those? Okay, just multiply. Okay. Any question? If no, then we go to a little bit how this related to probability. Okay. So this kind of problem is often appear in probability textbook. Okay. Is the question like you ask a very complicated question like this. Okay. You roll a die twice. What is probability the sum of the value is less than 12? Okay. Then what you have to think, okay, what is less than 12? There are many outcomes, right? Because you have to think about how many outcomes are there, right? You think about add up to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So there have many outcomes that is favorable to less than 12, right? Can be 1, 1, 2, 1, 1, 2, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, and then many outcomes, right? You try to count there actually 35 of them, okay? But if you are actually counting, then will be prone to error. Okay. So what we're going to do is actually find the complement. Okay. Because less than 12, the complement is more than or equal to 12. Okay. And actually, this is what we have here, right? We want to have event is less than 12, right? Which is difficult to find. We can find what is a complement is less than 12. And actually only one outcome there, right? Only one outcome there is only 6 and 6, right? And the question is how many outcomes are there in total, because we roll a die twice. The first die is 6, the second die is 6, so 6 times 6 is 36. Okay, so that's why the probability of a complement is 1 over 36, right? Because you only have one possibility, which is 6 and 6, and overall there are 36 outcomes in total, so that's 1 over 36. And complement rule tells you that you can just minus this, give you 35 over 36. Okay. Here, probably you would think still something not worth doing. But the question is, I only asked you to roll the die twice. Okay. What happens if I ask you to roll the die 100 times or 50 times, 10 times? Okay. And you will easily see that if I ask some question less than or bigger than some number, and then that the number of outcome can expand. Doing the complement rule is better, right? And here I tell you the counting will comes convenient, right? This is how you get 36, right? So it's 6 by 6. Okay, is that okay? I hope that this should be no problem. Okay, and here becomes a slightly difficult one. Is called the permutation. We'll learn this permutation, and the few slides after we learn combination. Okay, these two belong to the study we call combinatorics, how you combine things and count things. And since we are not math class, so we just talk about very simple application. And if you learn M1 math in Hong Kong, then it will be there already. But I try to assume no one have any knowledge on this. Okay. So actually what permutation is doing is you are trying to arrange objects in a linear order. Okay. So that's queuing. Okay. How many ways to queue? Okay. And the question we're asking the first is, suppose we have n balls, okay, in a urn or in a bag. Okay. So you are trying to print out one by one, put it on a line. Okay. And on the line means that who is in the first, who in the second would matter. Okay. Suppose you have 2 balls, 1, 2, and 2, 1 are different. Okay. So the question would be, how many different ways to have the result. Okay. So to think about this is maybe I try to draw it here. Okay. The question is, you have ball number 1, ball number 2, ball number 3, up to ball number n. So the question is, you try to have this ball, but how many different ways to rearrange them? Okay, because you use up all the balls, right? So you try to basically close your eye, pick up one ball there. Okay, what is the outcome? Pick up ball one by one. Okay, and you record the result, right? Suppose maybe the first draw you have 1, 3, 2, so on and so forth, right? Second draw maybe you have 3, 10, 5, okay. You have to draw every ball out of it. You're asking how many different ways how many different kind of way to do it. Okay. So how to do it is actually we follow the principle of counting. You can imagine that it's an n mission, okay, n task mission. Okay, the first task is to put the ball in the first box. Okay. How many different ways to fill up the first box? Okay. There are n balls there. Okay. Then that means that there were n different ways to start. Okay. N. And for the second box, how many different ways to do it? Will be n minus 1. Right? Because after you put the ball there, then you're gone. The ball is gone, so it's n less than. There will be 1 less. So on and so forth. n minus 2, until you have the last one. Okay. So then through the principle of counting, you just multiply them, is the answer. So that's end up in n factorial. Okay. So if you are not really convinced by this, another way to motivate that, right? You can draw a tree diagram. The first draw, you can have 1, can have 2, you can up to n. So the first draw, you have n different way. Okay. And say for the first draw, once you draw 1, you can no longer draw 1 again, right? So you only have 2, 3, up to n. Okay. And you have the second draw, you actually have 1, but you cannot have 2, you have 3. You can go on up to n. Okay. So that means that your first, no matter how many ways you can do it, the first one is n, right? The second one, how many ways you can do it? For each one, it is always n minus 1. Okay. There's no change. It's regardless of how you do the first one, it's always n minus 1. It's 1 less from the previous step, right? So that's why it's n times n minus 1 times n minus 2, so on and so forth, up to the last one. Okay. I hope that is clear why we have this statement. Okay, you can apply it from the idea of a tree diagram. Okay. Now here we comes the main definition here is, suppose you are not going to put all the n ball here, we just put our ball. Okay. So we have n ball, but we have our boxes. Okay. And we try to put in the boxes. Okay. So instead of, just go back to the whiteboard. Okay. Here with all the n boxes, we put n ball to the n boxes. But now the question is like, we actually only have our box. So we have ball number 1 up to 2 up to ball number n. But instead of all the n box, we have just how many of them are our boxes. So this box number 1, box number 2 up to box number r. Okay. So we're asking how many different ways to do it, right? So the first one will be just n way, right? Because it's n, right? N ball. The second one is n minus 2, n minus 1, right? And what is the r will be n minus r plus 1. Okay. Some of you may feel awkward here why it's not r, because the first one you can consider is n minus 0. That's how you count. Okay. You start from 0, n minus 0, and then you have to shift a little bit. Oh, sorry, it's r minus 1. Okay. So because 0 you count to r minus 1 is actually r, right? So that is how that's why we call, when you multiply this, okay, that is why what we call the NPR. Okay, it just, this is same as n times n minus 1 times n minus r minus 1. Okay, and here we write it in an easier form. Okay. Why? Because let's consider the following. Make our life easier. Is we multiply this, we continue to multiply n minus r, okay, and keep going on to 1. We must n minus r Okay. We multiply by the same in the numerator denominator. Okay. And it turns out this guy, right, it's just n factorial. Okay. And this is n minus r factorial. Okay. So that's why the formula is being NPR is n factorial over n minus r factorial. Okay. So this is why you can see the formula in the slide. Okay. It just make calculation easier. Is that okay? I mean, many of you might have learned in the high school, so, but in case you don't know, I just slow down. Okay. Let's see the example. Probably you will see. Okay. I mean, why we have that. Let's see example before the break. Okay. So this is a very simple example. Okay. This again motivated by a my also personal experience. Okay. So probably I don't know whether you have been to US. I mean, that's how I spent 5 years in Boston when I studied my doctoral degree. And again, student is very poor. I mean, you can imagine. I mean, unlike some of you, maybe from a very rich family. I mean, of humble origin. And in that case, I go to US. I mean, you have to think about money when you try to eat, right? And one of the cheapest thing you can get in US is sandwich or burger. Okay, Subway is one thing that can. I don't know, Subway is a little bit expensive here, but in the US it's rather cheap. My McDonald's is much cheaper than here, so I eat sandwich, okay, to save money. And in that case, some of the time, I mean, sometimes most of the time I cook, but by myself. But sometimes you don't have time, so you have to eat sandwich, okay. And there are several types of sandwiches, and there are 3 types of bread: white, Italian, whole grain. But actually more than that. There are many types, but just put 3. But there's say honey, oats, the many things. But suppose there are 3 types of sandwich, okay. And luckily you can put 2 ingredients there, okay. Maybe veggie or beef or egg mayo, chicken, tuna, or tomato, okay. And you go to you can put stack up, right? They will put the bread and you can put the thing and go on and stack up a little bit. And we're asking how many different ways to put a sandwich, okay. And for many people, or if me, I would think if you put beef on the top of a chicken, or we reverse it with different, because the sauce actually follow from the gravity, right? You have some sauce from the vegetable, then you will fall down, okay. So unless you're eating the sandwich in the space, okay, there's a gravity. So I think they're different, okay. If you think they're the same, we'll talk about that after the break. But if you think the ordering of ingredients is important, then we use permutation, okay. So the question is how many different ways you can eat this, right? Again, the same thing as here is principle of counting, okay. So regardless of how you do it, actually there are 2 tasks here. First task is choose the bread. The second task is choose ingredient, okay. And the 2 are independent, right? It doesn't matter how you choose an ingredient, and the bread are independent things, so you just multiply, right? There are 3 ways to choose the bread because there are 3 different kind of bread. And how many ways you can choose ingredient? You're choosing 2 out of 6. And you do remember the order ingredient is important, because the sauce from one ingredient can drop to the other, right? Because tomato, you cut it out, the tomato sauce can fall onto the thing, right? And or vegetable can be wet, so you just have to think about that. And in that case, it's 6p2, right? Because you are choosing 2 out of 6, so that's why 6p2. Okay, 6p2 is either 6 times 5 or 6 factorial over 4 minus 2 factorial. Okay, so we just 6 times 5 times 4 times 1, and this is 4 times 3 times 2 times 1, right? So cancel out. Let's left 6 times 5. So 6 times 5 is 30. 30 times 3 is 90. Okay, so already very good. The sandwich can already, I can have different combination for one semester, right? If you're lucky, you get some soup, then already even more than that, you can get the whole year. Okay, so that's how you count number of sandwiches you can make. Okay, and later, if you care about the ingredient, you think they're the same, the order doesn't matter. We talk about that after the break. We will call, that's what we will do in the combination. Okay, but let's a break of 10 minutes, and then let's see. In the meantime, I go around. I'm sure some of you may have problem of the base rule, but let me know. Okay, I go around. So let's resume. So it seems very happily and most of you understand permutation and the counting without any issue. Okay. So here is the final thing we want to talk is combination. And combination is a thing actually we will be using in very importantly in the next topic when we talk about random variable. Okay. So here combination is very similar to permutation. Okay. Permutation, remember here is we have n different balls. Okay. They're our box. We try to pick out how many ways you can put in the box. Okay. And in this case, the our box are order, right? What is in the first box or in the second box? Okay. It's important. Okay. If you put the ball number 1 in the first ball, first box, put number 2 in the second box, will be different from if we swap them. Okay. So what is in which box is important. Okay. But in some cases, what is it? In the numbering of the box doesn't really matter. Okay. So we don't care about which ball in which box. Okay. You just care about whether they are picked. Okay. And in that case, we will call combination. Okay. So that means that again the same idea. We have 1, 2, up to n box. We as n ball. We also have our box. Okay. The our box here. Our boxes. Okay. The question is being that you don't really have names on the box. Okay. The only our boxes. You just put them out. Okay. We don't put them aligned. Okay. We just basically put the ball, take out the ball, and just put it somewhere there. Okay. You don't order them. Okay. You just fill up. Okay. A mountain, fill up a there, just put there. Okay. You don't take the order. Order doesn't matter. Okay. They're not forming a line. Just like we are taking people. Okay. To form a team. Okay. In that case, it doesn't really matter which one we pick first. Okay. Now, let's see the way you calculate. That is something we really have learned it, almost or learned it. Okay. The answer lies on actually is this formula. Okay. So what we call this is called NCR. Okay. And this formula is like this. NPR is NCR times R factorial, okay, or NCR times RPR, okay, because RPR is R factorial. So you may ask why this formula works, okay. So we can understand this from 2 perspectives, okay. So we can start from the idea that, okay, remember our NCR is what we want to find, right? How many different ways to pick up the ball, and we don't care about the order. Okay. And for each way, okay, you don't order them. Okay. Suppose you pick our ball. Okay. How many different ways you can rearrange them, which is RPR. Okay. So that's why when you multiply, you have NPR. Okay. So I repeat the argument again. Okay. So how many different ways you can pick things? Okay. Without order. Okay. That is NCR. That's something I want to find. Okay. Okay. But for each way you do it, okay, there will be RPR way to rearrange them. Right. So for each, you pick our ball, give you our different balls. Okay. How many ways you can rearrange it? It's just RPR, right? Our ball, you just put them there. Okay. And this, why you multiply? This is coming from multiplication rule. Okay. So the question is being, you divide this task into two arbitrary ways. Okay. Here we do things like how many ways to pick our ball from n balls when you order them. Okay. This is direct calculation. But you can also do it in two steps. Okay. You can just pick up balls there. Okay. Pick up our ball and rearrange them. Okay. So that's why we have two steps here. And you multiply, give you this answer. Okay. So this is the first way to justify this formula. Okay. The second way to justify this formula is from the other dimension. Okay. So suppose you actually pick our ball of n balls. Okay. And if you want to arrive at our answer, actually you are duplicating, right, the overlapping calculation, right? Because for each ways, okay, and there are factorial different way to duplicate, okay, or RPR duplication. So you divide it by number of duplication you got, get you the answer. Okay. So I don't know which way fit your mind. One is removing duplication, right? The other is you, from the principle of counting, you divide them into two steps. Okay. Regardless of that, you just NCR is just coming from this formula. Okay. And probably you ask this formula. Let me show it again why this is right. Why this formula is right, but because it just NPR R factorial, okay? Because NPR is just n factorial over n minus r factorial, okay? And the denominator is here, so r factorial. Maybe just erase. Okay. So that is how you arrive what we call the NCR. So both NPR and NCR already appear in your calculator, right? So that shouldn't be an issue. Okay. Is there any question? Any question? Okay. Okay. Let's see this question. Okay. So if you go back to this one, if you really want to say this is not, you don't distinguish the ordering of ingredient, then just change N6P2 become 6C2, right? Then that will be the, what will the answer? 6C2, then would be 3 times 6C2, right? In that case, it's 3 times 6 times 5 over 3 times, sorry, 2 times 1, okay, 45, okay. So if you don't care about it, it's 45, right? But actually you can do it without thinking, because because the ingredient only have two, right? You can, every ingredient actually duplicate once, right? You can pick, for say, if you pick vegetable and beef, right? You can have beef and vegetable, right? So that's why everything is double counted. So you just divide it by 2, then done. Okay, so I hope that would convince you this is right. Okay, and finally, this one example also coming from when you go to Hong Kong restaurant, cha chan teng. So this is what you get in the breakfast. Actually, I think you do. And also, this is motivated from when I was, I think, in the high school. So that is what you get from the morning. So you can get 2 dishes, rice or noodle, or rice, noodle, and noodle, right? And then you will choose 2 or 4 dishes: sausage, spam, ham, or egg, 2 kind of sauce, black and white. Okay. In that case, you can easily see that because a bowl of dishes, right? You don't really distinguish you have sausage first or ham second, because always put in the same plate or the bowl, right? Whether the sausage on the left hand side or the ham on the right hand side, because the bowl is a circle, you can just rotate. Okay, so we don't really think they will be different. Okay, so that's why you can choose dishes. That's 2 dishes, right? You choose 2 out of 4 ingredients, so that's why C4C2, okay, and multiply by 2, okay, and 4C2 is just 4 times 3 and 2 times 1, okay? And that gives you 24, okay. So that is enough for a month, right? You exclude Saturday and Sunday, right? So they're already enough for you don't need to worry about the rotation. All right, so that is how many you can figure out. Is that okay? So so if this is okay, then we will go to one application that we will actually use it. Let's go this one first. So this one will be the thing we will be using a lot of time later. So suppose we toss a coin 4 times, okay? Asking what is the probability exactly 2 tails, okay? So this one is slightly a little bit difficult, right? Because there are 4 outcomes. Okay, so there are 4 times of toes, okay? And the first thing we need to figure out is how many total possible outcomes you can have, right? Because each toast have 2 outcomes, and you toast 4 times, so it's 2 times 2 times 2 times 2, so 2 to the power 4, 16. Okay, I don't think you have issue there because it's a simple principle of counting. So the difficult part lies on how you get exactly 2, okay? Because 2 can appear in the first, appear in the second, appear in the third, appear in the fourth, right? And you need 2 of them, okay? So of course you can draw a tree diagram like this, okay? Something you can do in a brute force way, or a naive way is, okay, you just start from here, head or tail, second one, head or tail, and third one and fourth one. There was 16, right? And then you just count how many of them actually have exactly two head or 2 tail, right? So that might be doable, okay? I mean, if you only have 4 toes. If you have more than 4, you have 10, then I don't think you can draw it, all right? So how do we think about that, okay? Is there any general way to do that? Because this is so simple, there's only 2 outcomes, right? So is there any way to figure out how to figure this out, okay? And we'll use the idea we'll just learn, combination, okay? So let's try to see what kind of outcome we can get here, okay? So actually you have the outcome can be represented by 4 letters, right? Can be, say, tail, 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 right? Can be tail, head, head, tail, so on and so forth, right? Can be anything, right? Can be head, 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 head. Okay, can be anything there. Maybe I change it to maybe I change it to like this. I just change each time. I just change a head first. Okay, so there will be 16 of them. Okay. So how is there any way to count this thing in a easier way? Okay. I think we are counting how many number of what's the question? How many number of tail? Okay. So we can represent this using the idea of the balls. Okay, just learn. Okay. So because we consider tail, okay, we just only count tail, right? We consider tail problem. Okay. So we can basically from the following. Consider we have 4 different balls. Okay. The ball have number 1, 2, 3, 4. Okay. 1, 2, 3, 4. Okay. And we will say, okay, if I see tail is equivalent to the idea that I actually draw 4 balls out of this. Okay. There are 4 balls on the table. Okay. I pick all the 4 balls, which means that I have tail. If I have first 3 are tail, actually I'm actually drawing the balls 1, 2, 3. Okay. If I have outcome, say like tail, head, okay, that means that I'm actually drawing the balls 1 and 3. Okay. And for last case, actually I'm not drawing any ball, no ball. Okay. If I have any ball there with number, which means that outcome is a tail. Okay. Just another example. Final example is I have tail, head, tail, equivalent to I have ball 1 and 4. Okay. So that means that by looking at what kind of ball I'm drawing, okay, in this 4 ball case, same as this, all the possible outcome in the contour thing. Okay. So now the question is being how many outcomes that actually I have 2 tail, right? That actually I'm asking out of 4 balls, I'm drawing 2 balls. Okay. I don't care about order, right? 1 and 2 same as 2 and 1, right? So that's exactly why we have 4C2. Okay, 4C2 actually is 4 times 3, right? 2 times 1, which is 6. Okay, so there's 6 different ways to do it. Is that clear why this is 6? It's clear because for each possible outcome, okay, I can represent it by looking at the balls. Okay, which ball is being drawn? The ball you have drawn is actually mean that outcome is a tail. Okay, if I draw 4 balls and 4 outcome are tail, if I only draw ball number 1 and 4, which means that the first draw and the 4th draw are tail. Okay, the ball are not drawn is actually head. Okay, so you understand how they associate together. That is the main key to understand what's going on. Okay, if there's no issue, then we actually can go back to the question. Okay, and we'll use this later when we talk about binomial distribution, but that would be something we talk about next week. Okay, so that's why we have 4C2 is 6. Okay, so that's why you have 6 over 16, which is 3 over A. Okay, so that is how you can do it. Don't worry if you don't fully get it, but I think we have something similar in the assignment, so you actually will have to work on it. So because this is very important, we will be using this for the next class. Okay, is there a question for this? I mean, it's not easy to understand. At least for me, when I first learned it, I feel a little bit tricky. I think it took me several hours to figure out what was going on there. But hopefully for you, you take much less than I do. Okay. If there's no question, finally, I want to talk a little bit more about. Yeah. Finally, I talk about this. Okay. Maybe better to the typo correct. So when we have actually with and without also fine anyway. So actually how we use permutation combination, I mean it's more technical, but later you will see when we talk about sample with replacement, then principal counting will be very useful. And that's how you count what kind of sample you get, then that will be something very useful. And when you talk about sample without replacement, depend you are doing ordered sampling or unordered sampling, then combination of permutation will be very useful. Okay, this is just technical because we don't talk about sampling issue in our whole course. If you want to do it, it will be other course, but that gives you idea why this is also important in the future. Because the thing we learn in this class is random sampling, and that actually imply we are in this regime. Okay? So each draw is the same thing, right? So that's why it's sampling with replacement. Okay, or you're talking about very large sample. You ask one guy, then you are not going to draw that guy again, right? So that means that you are doing sampling with replacement, and principal counting will be useful, right? And in that sense, it's more like independence, right? The counting things, you just multiply. But I guess I don't want to elaborate too much about here, just telling you that that will be related when you learn in the future, but not in our course. Okay, just mention that would be important why we're learning that. So there are links on the video in case you miss anything. You can go back to the video to learn it. It's a very small thing, and then of course you can ask me. Finally, the Excel. I'm not talking about this anything. I'm just telling you that there are several functions. In case you don't have the computer, sorry, you don't have the calculator, factorial is just Fn, fact n, NPR is just permute NR, combination is just combine NR. Okay. And a final remark is some of you may actually ask, actually in other class that you learn from other textbook, they would put this in this or this, they're the same thing. Okay, so that's the same thing. Just let you know. Some books would do in this way, but I just when you try to see that the same thing. Okay. I'm not going to go to the Excel to show you how to do it. I think it's very trivial. So I'm not going to spend time on that. Okay. So just to remind you what we have learned for this one is we learned the base rule, okay, how to update. And then we learned the combinatorics, principal counting, permutation, combination. Okay. And that we will use them. Okay. And although we don't talk about too much, the base rule in our class is have a lot of application, right? Because this is an updating idea, right? Just like you learn some information, how can you improve what we know? Okay. And this is something when you later try to learn machine learning, artificial intelligence, or all other advanced subject, that base rule will be things keep going, right? Because you can imagine that you have suppose you consider what we call nowadays a lot of people call algorithm trading, right? Just the machine keep trading. There's no human intervention or very little human intervention, right? And in that case, the machine keep changing the parameter, and how they learn. One way to do is the base rule. Of course, there are other ways, non-Bayesian, but base rule is still things that are very popular. Okay, and of course, non-Bayesian rule will be still related to this, but there's some other adjustment, but it's still similar to that idea. Okay, so this is a very basic thing that talk about learning. Okay, is there any question before we end our topic 2? The assignment will be released later today, but I mean, of course, you don't need to worry because it's supposed to release on Friday. But in case you want to take a look, then you'll be there later today. You'll be given 10 days from Friday to do it. Okay. Is that a question? If no, then we go to our random variable. Okay, random variable is a more advanced topic in probability. It's just like we get more structure into our sample space. Okay. So let's first define what is random variable. And well, actually, there's a very funny thing is I think I learned probability theory for several classes when I in college, and I go to intermediate class, and the professor asked everybody what is random variable, and someone in the front said a variable that's random. I mean, office is wrong, so it's not a variable that's random. I mean it's not variable, and itself is random is right, but it's not variable. That's random. Okay, so random variable in fact is a function. Okay, it's not a variable. It's a function. Okay, that assigns number to outcomes. Okay, so what it is just like maybe give example first. Okay, example first before I say why this is good. So example would be like the following. Just go a little bit further. You toss a coin. The outcome is either head or tail. Okay, so you are trying to say head can be a number, tail can be a number. So maybe you just say head is 1 million. Okay, tail will be 2,000. Okay, any number would do. Okay, just like each outcome I give a name, and the name is a number. Okay, that's random variable. Okay, let me repeat the statement is for each outcome in the sample space, I give a number. Okay, it doesn't matter whether meaningful or not. That's another issue, but it's just assigning number to outcome. Okay, you can assign 1 million to head, 2,000 to tail. Okay, whatever number you want. Okay, of course, this number have to be meaningful to be useful, but that is another issue. Okay, so that basically is what we are trying to do. Is one thing is we are trying to put numbers to outcome. So that's a function. Okay, function is just like you put something, you get you something, right? Just put the outcome, just give you the number. Okay, and you may ask why we want to do it. Okay, first we want to do it is because of remember if you toast the coin 10 times, right? How many outcomes you have is almost like 1,000. 2 to the power 10. Right? How you can draw the tree diagram is like very difficult. Okay, so if you consider a random variable, okay, and that actually simplify a lot. Right? Remember the scenario that you roll a die. Okay, roll a die. If you roll a die once, then you have 6 outcomes, right? And you roll a die twice, you will have 36 outcomes. Okay. But if you only care about the sum of the outcome, you only have end up with 2 up to 12, only have 11 outcomes, right? So instead of 36, you have 11, right? So that will make our life easier, right? Go back to the coin toasting, right? If you toast 10 times, what the total number of outcome? You have 1,024, right? Almost 1,000. But you just suppose you just only care about how many number of tail, number of heads you have. Okay, you only have 11 outcome, right? Come from 0 to 10, right? Only have 11. Instead of 1,000, you only have 11. So you reduce the sample space by 100 times. Is that clear? What we're doing is because of the sample space of the random experiment can be very large. Okay, so in order to simplify, we're trying to make it easier. Okay, so we just convert it to numbers. I mean, of course, we want to convert to meaningful thing. And when it comes to number, we can talk about statistics. We can talk about mean. We can talk about variance, which will be discussed next week. But the main key thing is to make sure that the things is more manageable, and we can do some calculation, right? Because looking at outcome, we cannot do many meaningful things, right? Then that's why statistics come handy in this case. because when things become number, we can talk about mean, median, right? We can talk about variance, kurtosis, skewness, right? And if this is categorical ordinal data, right, you cannot talk too much. Now, we need to define what we call support of random variable. Okay, it's just like the sample space, right? Sample space is all possible outcome, right, of the random experiment. Support of random variable is what are the value that the random variable can take, right? And usually either integer or real number, right? Or even a smaller set of integer, right? Maybe you just toss a coin once, you just either 0 or 1, right? You talk about tossing a coin 10 times, okay? You count how many number of tails, you just 0 from 10, only 11 numbers. Okay, this is the sum, this is support. Okay, is that clear? What's going on? See, random variable, just repeat, random variable is you put all the outcomes to numbers, and what kind of number you can put is called a support. Okay, and why we care about this is because of the type of the support is very important. Okay, whether the support is a discrete set or a continuum set. Okay, and that will make our life very different. The reason why the distinguish of this is due to the math tools we are going to use. Because when discrete means you can count those things in the support, right? There are how many, what kind of number you can put in. If they're discrete, okay, you can count it 1, 2, 3, 4, 5, okay? And the usual math you learn in the high school would work, right? Just addition, subtraction, multiplication, division, everything works, okay? But when you are continuous support, okay, that means that it's real number, right? Is any decimal number is also continuous, okay? In that case, the usual addition subtraction doesn't work very well. You need to use integration differentiation, okay? But don't worry, in our class, we don't require you to do any integration differentiation, except you want to understand some of the proof, but I mean, they are technical. So that's why in mathematics, you have to divide them into two, because all the tools will be very different, okay? So same as our class, we will divide them into two parts, okay? And we can't skip for the continuous, because the bell curve or the normal distribution actually is a continuous one, okay? And the one we used to see in the world, how many number of cases, number of customer coming, all these are discrete, okay? And there's an important theorem in statistics, which we don't prove, but we will say it out, is if you have many samples at the end of the day, a lot of things actually turn out to be normal or bell curve, okay? So bell curve is the main thing from this class, because the bell curve at the end comes out at the end, right? So that's why it's important. But if you don't have large sample, then you cannot use bell curve. So you really have to look at discrete. So discrete still have important, right? Because not all the time you can go to invoke those bell curve idea. Okay. So give you a more idea on what we call the discrete random variable. Okay. Discrete here means that you can count them 1, 2, 3, 4, 5. Okay. And that's what we call finite. Okay. And countable finite means that there's no upper bound, so can be how many consumer here can be 1, can be 0, 1, 2, 3, 4, 5 up to infinity. Okay, there's no upper bound there. Okay, but I think for you don't need to worry about that. Just like 1, 2, 3, 4, 5 is just discrete. Okay, and continuous is if 1 or 2 is okay, 1.5 is okay. If anything in the middle also makes sense, it's continuous. Okay, if not, if you pick any two value, middle is not meaningful, then it's discrete. Okay, I think that's the easiest way for you to think. Of course, it's not very precise, but it's enough for our class and for many other class also as well. Okay? Discrete is just like you pick any two value, the middle doesn't make sense, discrete. It makes sense, continuous. Okay, so I hope it's very clear. I don't want to go, and then usually in this case, you want to assign integer to outcomes. Okay? That is a usual way. Of course, you can assign some decimal number or fraction or anything crazy, but usually you want to assign something meaningful, right? Because you want to do meaningful thing. Okay. So let's go back to the example. We toss a coin once, right? It's either head or tail. Okay. So what is a reasonable way to put numbers to these two outcomes? Okay. You can put any number. Okay. But we decided to say X is a number of head. Okay. Of course, you can do number of tail, the same in this case, because either you head or tail. Okay. In that case, I would say head, we put head is 1, tail is 0. Okay. So in that case, the support of X is the rank or the sample space become 0 and 1, right? Just basically you replace tail with 0, head is 1, so it's just like 0, 1. Is that clear? So we just put numbers. Okay, for outcome we put numbers. Is that okay? So if you try to understand graphically, I mean, if you learn the high school, I guess this is something you see, right? Head map to 0 and tail map to 1. Is that okay? So this is the way function, right? This is usually people talk about function. Okay. And now the next thing is, suppose you toss the coin twice. Okay. And what are the possible outcomes? The sample space, you know already, is like 4 outcomes here. It's head, 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 tail, tail, head, tail, tail. Okay. And so the question is, what is the appropriate random variable? There are many ways, right? You can say number of heads, number of tails. Okay. Or you just randomly put 1, 2, 3, 4, right? You can just have no point, but it's possible you can just say 1, 2, 3, 4, sort of fine. But if you do this, it's not clear what you're talking about, unless you mean the gamble. If XX you get $1, XT you get $2, TX you get $3, TT you get $4, and this assignment will be meaningful in that way. Okay, so and I think the most useful way usually people would do is to say the random variable assigned according to number of head. Okay, so this one you assign to 2, right? And this one you assign to 1, and this you assign to 0. Okay, so this is how it's a random variable that happened, right? So that's why you have 0, 1, 2, right? Because TT is 0, XT and TX is 1, and XX is 2. Okay. So I hope that is clear what we're doing. So you just replace the outcome by numbers, and you can see it's not 1 to 1, right? So the 2 outcomes can assign the same number. Okay. 2 outcomes. Okay. But each outcome can only have 1 number. Okay. An outcome cannot have 2 numbers. Okay. XX only have 2. You cannot say 2 or 1. No, there's only 1 number here we are focusing on, because we're talking about we only talk about single random variable. We're not talking about more than 1 random variable in our main context. Is that okay? Is that clear what it is? Okay, just put numbers to, and the support is 0, 1, 2. Okay. Now, if that's okay, this is how the graphic means is. Oh, I think I have a typo. XX is 2, XT and TX is 1. Oh, this is 0. Okay, because I'm talking doing number of heads. Is that okay? Because I add this slide because last class I draw it on the screen, and they think I should have that on the slide, so that's why I put it there. If you download earlier, then you don't see this graphic. Okay, but I mean there's no change in the slide except this only addition. If you download the earlier version, it shouldn't make any difference. Okay, but okay. Now we talk about continuous random variable. I just mentioned continuous random variable appears when the random variable we try to assign. Okay, if you assign value 1 and value 2, value 1.4 also makes sense. Okay, any value, you find anything in the middle, If all makes sense, anything in the middle makes sense, it's continuous. Okay. So continuous random variable, actually we have a lot of scenario, especially talk about business application. Many of the time, actually we're trying to measure already, it's already a number, right? You look about temperature, right? Is already a measure, give a number already, okay? Or stock price is already a measure there, okay? And in that case, right? And here we have real number, and then we put the number bigger than the absolute zero, okay? That is the number, and the notation is this characteristic R is called real number, okay? And R star is the set of positive non-negative real number. We put it here because this is a usual way people write it, okay? I put it there because in case some of you try to read textbook, then you sometimes you see this, okay? So I just do, but we will not use it, but I just put it there to let you know how you can write this. And when I stock price in this, okay, that will all non-negative number, so it's R plus, okay. So that is the support, okay. And do note that in both cases, right, the sample space is same as support, right, because the thing you are measuring is already a number, okay. So already it's actually a random variable itself, okay. If you try to measure something, it's already a random variable, right? Because when we talk about, say, this is, say, stock market index, right? What is it capturing? It's capturing the performance of major stock of all the stocks, okay? Say Hang Seng Index. It's capturing, I think now is 70 something stocks in Hong Kong, right? And you already summarize a number there, okay? Okay, you don't care about how different stock is behaving, but at the end, there's a one number comes out, okay? So this one is already a random variable, okay? The sample space is all the 70 stock, how they perform, and you have some way to summarize it to become a single index, okay? That is already a random variable when you try to measure things, okay? So that's why for when you look at numbers already captured in the world, usually it's already a random variable, so you don't need to worry about the difference between sample space and random in the support of the random variable, because usually the same for most of your purpose, okay? But for you have to distinguish them, right? But there's a ton, okay? So before I end, I want to talk about a little bit about discrete random variable, okay? So how to describe a discrete random variable? There are two ways. Actually, there are more than two, there are many ways. But the first way we do is very simple. It just tells me what is the value you are trying to pick and what the probability, okay? So in the case of tossing a coin, right? We have a tossing a coin once, head or tail, okay? Remember, it's a sample space, right? And we say number of tail is either 0 or 1, right? It's either 0 or 1, right? And we know that when we try to draw this, right? X is 0 or 1, okay? And what is this function is telling you f of x. F of 0 is probability x equal to 0 is 1/2. X is 1 is 1/2. Okay, so that is what Px is. It's telling me that you give me the value, okay? I tell you what's probability that that random variable is, right? So remember, this is actually referred to the outcome, which is number of head, right? This head, this is tail, right? If head is 1, tail is 0, and probability of 1 is probability of head is 1/2, right? So basically, just like what you learn from the probability of sample space, you convert it to the probability in terms of random variable. Okay, let me repeat the statement. Okay, for each outcome in the sample space, right, your probability, right? And the question is asking now, we're not talking about sample random variable. We talk about events in the sample space. We talk about random variable, right? So we want to know how they're defined. Okay, just what is this number there? Okay, so of course we'll talk about more about next class. So see you next week. I'll make sure that you submit your homework on Friday. Okay, have a nice weekend.